In the last video, we endeavored to create definitions of numbers and categorize them into sets by their definition. Um, and the sets that we came up with were the natural numbers, which start with 1 and go on infinitely. Then we add to that 0, we have the whole numbers. Whole numbers start with 0 and then go on positively infinitely. When we include with 0 the negative numbers, we now have the integers. So integers are whole numbers and their opposites. They include 0 even though 0 is neither positive nor negative. Uh, in between in between these integers there are numbers that we can represent as ratios, or decimals that either terminate like 2.25 or repeat like 0.3333 repeating, right? 1/3 basically is this number here in decimal form. This is an approximation of that. Those are going to be called rational numbers. And the corollary to those, or the opposite of those, are irrational numbers. And remember, for our purposes, we're not going to, this is an arbitrary distinction for our class, although it is a real distinction. And if you want to learn more about math or group theory or number theory, you can talk about transcendental numbers and real algebraic numbers. But for the most part, we're just going to blur this line here. This line doesn't really exist. And we're going to call this whole group irrational numbers. These are all irrational numbers. So with that in mind, we are asked to, given a set of numbers, and I'm going to change this just a little bit. I'm going to put, wow, that's a little thick. Let's try a little bit thinner of a brush size for that. I'm going to put squiggly brackets around these sets of numbers, and that's going to give it what's called roster notation. Roster notation occurs when you have a set of anything really inside squiggly brackets, right? So here is my set of numbers, and when I put it in squiggly brackets and separate each member with a comma, what I'm talking about here is a roster notation. We will contrast that with something called a set builder notation, which also makes use of the squiggly brackets, but it talks more about the characteristics of the number. So when we're talking about a set of numbers, we can say the set of numbers x such that x is a positive odd number, say. And that will mean numbers like 1, 3, 5, 7, and so on. What this does for us is it tells us, it says in these terms, the set of, and in this case we're using x. And this little line here, this little line, vertical line, tells us such that, and then we have the characteristics of the number afterwards. So I just changed a little bit of this question group just so that we can see what roster notation looks like, because you're going to be asked to identify a little later roster notation. So here's our set. We've got -6, 0, 1, -1/2, -4, 7/9, and so on. And we're asked to name the natural numbers. So remember, natural numbers are this group here. They start with 1 and they go on infinitely. So with that in mind, -6 and 0 are not natural. I'm going to go ahead and put this in roster notation again. 1 is a natural number. Negative, negative, a rational number. 12 is also a rational number. A natural number. Negative, fraction, decimal, no, no, no. Square root of 3, no. Here's an interesting one. This is the square root of 25. Now, whenever we see a number like the square root of 25, this symbol here tells us to take the principal square root or the positive square root. So for that, we're going to say that the square root of 25 is a positive 5, and that's a counting number. That's a number that we use to count with. So we're going to also call that one we're going to also call that one a natural number as well. And I think we're done. I think that's all of our natural numbers. The rest of these we'll go through a little more quickly. Number 2 says name the whole numbers, and so basically we're looking at the same set of numbers here, except that now we're going to include 0. So all those numbers that we had before, now including the 0 because it is a whole number. Number 3 says the rational numbers, and so for us the rational numbers are going to be, let me give us a little more room, basically everything here, all of these numbers can be represented as a ratio. Even 0 can be represented ratio. 0 is 0 over any number. Negative 1/2. Ratios can be positive or negative. Negative 4, I'm running out of space. 7/9 can be, that's also 12. I'm just going to go down to the next space because I've run out. Negative 6 over 5, 3.45, 5.5. Basically all the numbers that we have here. As far as the rational number goes, it's going to be everything except that's not a rational number. The square root of 3 is not a rational number, and this is not a rational number. It looks like there's a pattern there, but because the 3's keep growing, it's not repeating. It's not a repeating pattern. So neither of those are rational numbers. Everything else here, and I just ran out of space, everything else there is a rational number. Okay. Name the integers. Well, the integers, there's fewer of those, so I'll go ahead and write those down. That's negative 6. 0 is an integer, remember. 1, negative 4, 12. Square root of 25 is also an integer. And I think that's it. So you get the point. You get what's going on here. Real numbers, all of them are real numbers. The whole set is a real number because none of them are the square root of a negative number. And the irrational numbers, we only have 2 of them. Here it looks like that'll be the square root of 3 is an irrational number. If you don't believe me, put it in your calculator and see what it looks like. And 0.131331, so on and so forth. Those are our only irrational numbers. From here on out, I think I'm going to do the even numbers so that I can give you an opportunity to practice the odd ones on your own or in class or whatever. But this is building on our idea of roster notation. With roster notation, it's asking us to, in this case, number 14 says the set of all letters in the word are. So using roster notation, I'm sorry, in the word solve. So using roster notation, I draw my squiggly line, and the set of letters in the word solve are S, O, L, V, and E. And I close off my set. So that's set of the letters in the word solve. I could rearrange them if I needed to from lowest to largest. And while that would be okay, we weren't asked to do that. So we'll go ahead and skip that for now. This one says the set of all odd numbers, whole numbers, less than 13. So again, we use our squiggly bracket, and 1 is odd, 3 is odd, 5 is odd, 7 is odd, 9 is odd, 11 is odd, and it says less than 13. It doesn't want 13, so we'll close it off there. You get the point of what's happening here. Alright, now it's telling us to use set builder notation to name each set. So, okay, so let's use set builder. And remember, set builder, this is a roster. And remember, set builder uses a squiggly line also, but it says the set of, we'll go ahead and say X here, such that, let's see, 4, 5, 6, 7, 8, 9, and 10. So we'll say that X is a whole number greater than or equal to 4 and less than, we can just say less than 11. We could also say less than or equal to 11. And there's remember these are little interesting kind of groups. Greater than, these comparison, greater than or equal to, less than. These are interesting comparisons that we're going to get into. You should know how to do less than or greater than already, but we'll practice it just a little bit for fun. What about this one? The set of all real numbers. So the set of x such that x is a real number. Good enough. How about that? Anyway, that's a little bit of practice of the categorizing numbers and using roster notation and set builder notation.